Okay, we're on the rational function homework. So the first thing we need to do is find the domain of the rational function and identify any horizontal or vertical asymptotes. So as far as the domain is concerned, the main thing that you have to look at is the denominator. Are there any values of x where the denominator goes to 0? So if we look at the domain, what we need is x plus x2 minus x equals 0. So this is where the domain, where the function will not exist, when the denominator goes to 0 if the numerator doesn't go to 0. And the only way both the numerator and the denominator would go to 0 at the same time is if they had the same factors. So in this case, you don't have to worry about that. So if you subtract 2 from both sides, you get that, or x equals 2. So what we would say is, you could say all real numbers except x does not equal 2. That would make the denominator go to 0. Now you can have rational functions where you don't have any vertical asymptotes. The next problem is probably an example of that. Okay, so the other things, horizontal asymptotes. So there are those three rules. You look at the highest order term. In this case, it's a little tricky because the way it's been written, but I could change the order so that I have the x terms first, which are the highest order terms. The constants are the lowest order, and then you have x to the first power, x to the second. So both these are x to the first power, and because they're the same, the rule says that the horizontal asymptote, which is a horizontal line, so we're going to say y equals, you take the ratio of the leading coefficients. So again, just like the ones are implied when you just have x by itself, we also have the implied coefficients in front are 1. Okay, so if you don't see anything, if it's just x, then the coefficient is 1, and we have plus 1 in the numerator, and minus 1 in the denominator. So that reduces down to that. So the horizontal asymptote is a line y equals -1. And that's what the function will approach as x becomes large in both the x and the y directions. And then you have your vertical asymptotes, and your vertical asymptotes are very similar to the domain question, is what values of x do you get a 0 in the denominator but not a 0 in the numerator. So for the same reason we got the domain not equaling 2, we get the same thing here. So the vertical asymptote is also a line, so it's a vertical line. So here we have a horizontal line, y equals -1, whereas here we have a vertical line at x equals 2. So that's a 2, this is a -1. So when I ask for horizontal asymptote, I want y equals some constant, and vertical asymptotes x equals some constant. Okay, the second one. Now I said that this probably doesn't have a vertical asymptote, and the way you would determine that is if this doesn't have any real zeros. So if I wanted to look at x squared plus x plus 9 and find out the values of x where that go to 0, I just set it equal to 0. So what can I do? Well, I could use the quadratic formula, and if I got x to negative, well, if I ended up with the square root of a negative number, then I'd say I can't have any real roots. So let me just show you that approach. It's minus b plus or minus the square root of b squared minus 4ac over 2a. So instead of actually solving for it, if you're just looking to see if there are real roots, b squared minus 4ac is something. And if that number is less than 0, then you're going to have the square root of a negative number. So let's evaluate that. So we got b is equal to 1. That's the coefficient for x. A is 1. Coefficient in front of x squared. C is 9. So if we plug that in, you'll have 9 squared minus 4 times 1 times 1, which is 81 minus 4, which is, so actually you can get a root here. So maybe I'm can't always just assume things. You got to work through it. So in this case, I get the square root of 81 minus 4 is 77. So that's b squared minus 4ac. So anyway, that's positive. So there are real roots. Oh, no, it's not. Okay, I should have gone with my, so there you go. I know more than I think I know. I put wrong numbers in here, so let's do this right. Okay, so you get b squared minus 4ac. So there you end up with negative 35. Okay, so since that's negative, since that's less than 0, not less than or equal to 0, it could be equal to 0, but it can't be less than 0. So because the argument here, the square root is less than 0, there are no real roots. And as a consequence, the domain in this case would be all real numbers. There are no vertical asymptotes for the same reason. There are no values of x where the denominator can go to 0. And then as far as horizontal asymptotes, in this case it's already set up. It's got the highest order term, which in this case is 3x squared and x squared. So you take the leading coefficients. So you say y is the ratio of the leading coefficients to the highest order term, which are 3. And it doesn't say it, but it's implied 1. So the answer is y equals 3. And let's open up my graphing program just to show you what's going on here. We'll do both of the functions that we've just done. So this is 2 plus x divided by 2 minus x. So we said there was a vertical asymptote at 2, horizontal asymptote of -1. So let's see if that's true or not. So let's draw the line y equals, our horizontal asymptote would be y equals -1. So we're just going to type in y equals -1. So there's your vertical asymptote, your horizontal asymptote. Your vertical asymptote would be a straight line up and down, which we can't draw here. So you see it 2, and if we zoom out in the y direction, you can see how the functions approach positive 2. And if we go back to our standard zoom and we zoom out in the x direction, you can see that the function approaches -1. Okay, so that agrees with what we just came up with. And the second case, we have 3x squared plus 1 divided by x squared plus x plus 9. And we shouldn't see any vertical asymptotes here. And let me do my standard zoom here. So you can see that there are no vertical asymptotes. If I zoom out in the x direction, you can see there's no place where it goes to positive or negative infinity. And you can also, if we put the line y equals 2 in there, you'll see that, or is it 3? No, it was 3. Y equals 3. 3. You can see as we zoom out in the x direction that the function approaches the line y equals 3. Okay, so that's domains and vertical asymptotes. Okay, the next one, find the zeros of any of the rational functions. So when it comes to zeros, you just set the numerator equal to 0. So for asymptotes, you're looking at the denominator. For zeros, you look at the numerator. So we can ignore the denominator. So for zeros, when does the numerator equal 0? So the numerator is x cubed minus 8. And okay, so how do we find out what these zeros are? Well, you know, this kind of looks like x cubed minus 1, except instead of 1 we've got 8. You might remember that's x minus 1 times x squared plus x plus 1. That's back from algebra 2, I think. So it seems like x minus 2 should be the answer, because the cube root of 8 is 2. Well, let's see, to see what's left over, let's use synthetic division. So you get 1, 0, 0, negative 8. And we said we think a 0. So remember factors versus zeros, we had x minus 2 times something. That's what we're trying to figure out. So the 0 is x equals 2. So we're going to use the 0 here. So bring down 1. 2 times 1 is 2. 0 plus 2 is 2. 2 times 2 is 4. 0 plus 4 is 4. 2 times 4 is 8. Negative 8 plus 8 is 0. So, you know, here we said we had x minus 1 times x squared plus x plus 1. So you can't just put in 1, 1, 1. That only applies because this last thing's 1. So that's one reason we need to do this. So what you have left over is x squared plus 2x plus 4. Now, so what we can do is we can rewrite x cubed minus 8 as x minus 2. That's the factor associated with that 0. And then what we have left over is x squared plus 2x plus 4. So the question, are there any real zeros? Now, one way to make you worry about, think about this is, if this is positive and this number is larger than the middle number, it's time to think about it. So we looked at just a minute ago, we said if b squared minus 4ac is less than 0, no real zeros. This looks like a case where that could happen, so let's try it. So again, we have a is equal to 1, b is equal to 2, b is equal to 2, c is equal to 4. So we plug that in, we'll get 2 squared minus 4 times 1 times 4, which is equal to 4 minus 16, so that's negative 12. So no real zeros, because negative 12 is less than 0. So that means that there's only one x-intercept. So what we could say is the x-intercept is the coordinates 2, 0. You know, this is the 0, this is the factor. This is the x value, this is the y value. Okay, let's plot this thing just to show you what it looks like. One thing, notice that the denominator has no real zeros either, because I have x squared plus a number. So if I tried to solve for x, I'd have x squared equals negative 1. Can't take the square root of a negative number. And again, this one only gives me, when you factor it, you can only get one real 0. So let's put standard zoom here, and we'll get rid of the old stuff. So we put x cubed minus 8 in parentheses divided by, in parentheses, x squared plus 1. Now I have to put it in parentheses, even though over here they're not in parentheses, to show that this entire x cubed minus 8 is in the numerator and x squared plus 1 is in the denominator. Here it's obvious because of the way I've written it. So there you go. There's the x-intercept at 2. And it looks like that you might have vertical asymptote in here because it looks like it's going that direction. But let's zoom out, and you can see it doesn't. Okay. So sometimes you got to zoom out to make sure you're making the correct conclusions. So this has one x-intercept at x equals 2. It has no vertical asymptotes. Okay, now we're getting to, just looking to see what else we got to do here. Okay, so now we get to the nitty-gritty here, which is finding all these things. So we need to identify intercepts, set the numerator equal to 0, solve for x, find any vertical or horizontal asymptotes. So vertical asymptotes, we set the denominator equal to 0, see if there's any values of x where that occurs. Horizontal asymptotes, we use the rules. Check for symmetry. Yeah, so what does that mean? And I always kind of don't talk about that much, but I'm just trying to see if there's anything in here that gives us more insight. Let's see what they have to say. So I'm just reading. Yeah, it's funny because they don't even include it. I don't know why they put it in there. Yeah, so yeah, there's a few cases. Most cases there is not symmetry. It's only a few special cases. So for the most part, we won't talk about that, and I'm not going to test you on it. Then it says plot additional solution points as needed. So once we plot all these other things, we might say, oh, let's pick a value of x that might give us a better idea of what the heck is going on. Okay, number 4. So let's start with A, intercepts. Well, if you look at the numerator equals 1. Are there any values where that changes from 1? No. Okay, so no x intercepts. So that's the x-intercept. Set the numerator equal to 0. The y-intercept, you set x equal to 0. Same thing we did in chapter 1. So if you look at that, we're doing g of 0, which is 1 over 3 minus 0, or 1/3. So the y-intercept will be 0, 1/3. That'll be a point. So let's put a little box around that because we can plot that. Okay, B, vertical asymptotes. So vertical asymptotes, we look at the denominator. And the denominator in this case is 3 minus x. So we want the values of x where the denominator go to 0. So if you solve for x, you'll get x equals 3. And if you think about it, if I plug 3 in here, 3 minus 3 is 0, so that checks that I did the right thing. Okay, so that means that, for one thing, the function does not exist at x equals 3. It also means that we have a vertical asymptote. So the vertical asymptote is a vertical line, which is x equals something, and it's equal to that. So that's my vertical asymptote. So I can plot that. Okay. Now, the horizontal asymptote, then you have to look at both the numerator and the denominator. So what we do is I'm going to rewrite this. I'm going to move the x term first instead of second. So, what's the order of these things? Well, here I have x to the first power. Now, I don't usually show this, but, technically I have x to the 0 power if you wanted to have something in the numerator. So a constant is just x. The constant is the constant times x to the 0. So since this number 0 is less than 1, this number here, okay, so that's where I get those numbers for. The rule says that the horizontal asymptote is the line y equals 0. One other way to think about this is if as x gets large, you're going to have 1 over a very large number. And whether it's positive or negative doesn't matter. You know, if you get 1 over infinity, that's equal to 0, or 1 over negative infinity equals 0. So both of those give you the same answer, which is 0. So that's my horizontal asymptote. Okay, check for symmetry. Yeah, what are they saying there? Well, what you could do is if you do g of x, that's the function. And if you did g of minus x, you get 1 over 3 minus a minus x, which would be 1 over 3 plus x. So g of x is not equal to negative g of negative x, or it's not negative g of x. So it doesn't really have symmetry around anything except around the vertical asymptote. So that doesn't really have symmetry. Okay, so now we need to plot what we know, and then we'll see if we can come up with some extra points that we need. So we're gonna get a piece of graph paper. One nice thing about rational functions is a lot of times you don't have to do crazy scales. You can just do minus 10 to plus 10 in both directions. It's the x-axis, y-axis. Okay, so let's plot what we know. The numerator never went to 0, so we didn't have any x-intercepts. But we did have a y-intercept, which is 0, x equals 0, y equals a third, which is going to be right there. Let's put a little red dot. Okay. Then we have a vertical asymptote at x equals 3. So we're going to draw a vertical line at 3, so that's your vertical asymptote. Then you have a horizontal asymptote, which is y equals 0. So typically I write, well, in this case I only have one vertical asymptote, so I can make it just one big line going horizontally like that. And that's it. Okay. So, you know, these reciprocal functions like this typically look something like that, or something like that. So you can kind of see what we've done. We've moved essentially we've translated the axis 3 units in the x direction. And because there's a negative sign here in the initial function, wherever it is, so the original, let me write it out here. Here it is, 1 over 3 minus, so this is negative, then you expect it to be flipped around. So it's going to be the green one. You know, it's going to be something like this, something like that. So the question is, you know, we at least have one point here. So we know that we have to at least come really close to the x-axis at this point. And then we're going to climb up. So, you know, how quickly does it climb up? So I would say let's evaluate the function here at x equals -1. And you could do the same thing here. So this is, well, sorry, not -1. That was a dumb idea. Okay, 1 unit here. So we'll do it there, which is going to be +2. And we could do the same thing over here. Maybe you pick 2. You could pick 1 over here. You would have some symmetry. So if you go 1, 2, 3 units, 1, 2, 3 units, I would expect the function to have that value or except on the other side, something like that. Because relative to this transformed origin, you expect the same thing to happen on both sides. And likewise with these numbers, once I calculate f of 2, it should be the same as f of 4. Let's just prove that's true, just before we get carried away with things. So, f of x equals 1 over 3 minus x, so f of 2 is going to be 1 over 3 minus 2, which is going to be 1 over 1, which is 1. So I could put that point in right there. And you could do the same thing for f of 4. That's going to be 1 over 3 minus 4, which is 1 over negative 1, which is negative 1. So yes, it is symmetric. So I can put that one down here like that. And, we're pretty close to the asymptotes. So I don't think we really have to do that much more. This is going to come through here like that. And then it's going to loop up pretty quickly. Go like that, up to there. It doesn't cross over. Likewise down here, it's going to come up from negative infinity. And it's going to then start to curve when you get close to here, and then go through there. Like that, it has to stay on this side. So what do we use? We use the y-intercept. We pick 2 points, 1 unit on either side of the vertical asymptote to evaluate the function. So with 3 points and 2 asymptotes, we did pretty good. Okay, next one. So again, intercepts. So we got 2 intercepts. We've got the x-intercept. That's where the numerator is 0. So all we do is just take the numerator, 5 plus 2x. Oh, yeah, we didn't plot the function from the previous example, so I'm trying to see how close this thing looks. So if we plot 1 divided by 3 minus x, and we look at the, if we zoom out in the x direction, so we see 10 at the limits, so that's about right, because we could go a little bit further. So there's 10, 0 to 10, and we could zoom in the y direction, so we get 10. So we get 10 and 10. And you can see, that matches up pretty good. See the horizontal asymptote is 0. The vertical asymptote here is x equals 3. So that turned out pretty good. Okay, back to number 5. So to find the x-intercepts, we set the numerator equal to 0. So you get 2x equals negative 5, x equals negative 5 halves. So we're going to say it's negative 5 halves, comma 0. So that's a point. It's an intercept. Then the y-intercept, you set x equal to 0. So you're valuing this function c at x equals 0. So you get 5 plus 2 times 0 divided by 1 plus 0. So we're just taking the function, and you get 5 over 1, which is 5. So that's my y-intercept. So I'm going to say that is going to be 0, comma 5. Okay, so that's another point. Next, vertical asymptotes. So that's B. The vertical asymptote is where the denominator goes to 0. Okay, so the denominator is x plus 1, so that equal to 0. You you get x equals -1. Okay, so that is your vertical asymptote. That's an equation, not a point. Then you have your horizontal asymptotes. And there you use the rules. So I'm going to, again, switch the order. C of x equals 2x plus 5 divided by x plus 1. So the order of the highest term, order term is 1. They're both 1. And so the horizontal asymptote is y equals the ratio of the leading coefficients of the highest order term, which are 2 and 1. So I get 2. So y equals 2 is my horizontal asymptote, which is a line. Okay, symmetry, yeah, that's not going to happen. So now we're going to get our piece of graph paper out. And let's see. Let's plot what we know here. Here's our x-intercept, -5/2. So this is -10, this is +10, this is +10, -10. So this is 1, 2, 3. 5/2 is 2.5, so that's my x-intercept. My y-intercept is 5. 1, 2, 3, 4, 5. Okay, so those are the points. Vertical asymptote at x equals -1. So I'm going to draw a vertical line at here. And my horizontal asymptote is y equals 2. So again, because I have only one vertical asymptote, I can just draw lines. Now I'm drawing as two parts because if I had two vertical asymptotes, then I'd just put them on the outside of the asymptotes. But because there's only one, you get just one continuous line. So you can kind of guess what's going on here. This is going to come down, go through this point, and then it's going to approach this line. Now, I knew it didn't go the other direction because if I came down here, I'd have to come back up, and that just wouldn't make any sense. Also, if I went down through the x-axis, I'd have to come back up, so I'd have two x-intercepts, so that's not going to happen. So I know in general it's going to look something like this, and likewise, it's going to do the same thing over here. So, what I could pick this point here, some point at x equals 2. I could do that. That might be a good one. If I did it here, x equals 1, then it might be too close together. So I'm gonna evaluate the function at x equals, let's see, 1, 2. That'll give me that point. And I'm going to evaluate this. I could either do it at this x value or this x value. So I think I'm going to go over here. So let's go 2 units. So this is 5/2. That's 3. Let's go to -1, 2, 3, 4. So we'll do evaluate the function at -4. So we got to remember what the function is, and it is 5 plus 2x over 1 plus x. So 5 plus 2x over 1 plus x. So that's the function. What do we call this thing? C of x. C of x. So what we want to do is C of 2. So we have 5 plus 2 times 2 over 1 plus 2. So that's 5 plus 4, which is 9. 1 plus 2 is 3. That simplifies down to 3. So I've got the point 2 comma 3. So that's one additional point. And then I can do C of -4. So that's going to be 5 plus 2 times -4 over 1 plus -4. So I've got 8, -8 plus 5. -8 plus 5 is -3. And 4 plus negative 1 plus negative 4 is negative 3. So I get 1. So the function here is negative 4 comma 1. So let's plot those numbers. Let's plot those. So you've got 1, 2, and 3. 1, 2, 3. So it actually turned out very close to exactly where I thought it might be. And then over here we go negative 4. 1, 2, negative 1, negative 2, negative 3, negative 4. And the function value is 1, which places you right there. So now we can sketch this thing in. This is going to come down from positive infinity. It's going to go through this point. It's going to loop around. It has to get some horizontal components so that it then approaches the horizontal asymptote. Likewise over here, we come from the horizontal asymptote. We start to curve a little bit towards that green point. We have to go through both the green point and the red point. And then we come down like this. And that's it. Okay, so let's plot this thing. So the function was 5 plus 2x divided by 1 plus x graph. And it's going from negative 10 to positive 10. You can see if I plot y equals 2, that's my vertical asymptote. I mean my horizontal asymptote. So there's my horizontal asymptote. My vertical asymptote is going to be x equals negative 1, which is going to be right here. And you can see it crosses the x-axis here at 2.5, negative 2.5. So that looks pretty good. Okay, the next one, what are we going to do? So the best thing to do for this third problem in this group is to create a rational function. So we got a constant and a rational function. So what we're going to do is we're going to find a common denominator. And the common denominator would be x squared. So we'll multiply and divide by x squared for the first term, which is essentially multiplying by 1. So we get that. So in the numerator, we'll have 2x squared minus 3 divided by x squared. So now we're going to look at that. So what are we doing here? Identify all intercepts. Okay, so we have the x-intercept. So we're going to set the numerator equal to 0. So if we add 3 to both sides, divide by 2, take the square root. So it's plus or minus the square root of 3/2. So we'll get our calculator out for that, because we're going to have to plot them on the graph, so we do need it in a decimal form. 1.5 is 3/2 is 1.5. So we want to take the square root of 1.5. And we get 1.22 plus or minus 1.22. Now, the y-intercept, you're going to set x equal to 0. So the y-intercept, just set y equal to 0. And what you would get, so you get f of 0 is 2 times 0 squared minus 3 over 0 squared. Well, that's undefined. And we'll see why in a second, because if we want to find the intercepts, I mean not the intercepts, but the asymptotes. So the asymptotes are, we set the denominator equal to 0. So the denominator is x squared equals 0. So what values of x make that true? well, x equals 0. Okay, so that's my vertical asymptote. So I didn't write that up here. Vertical asymptote. We set the denominator equal to 0. And so if we look at this y-intercept, that's why we didn't get a y-intercept, because at x equals 0, which is the vertical line, is the y-axis, the function is undefined. And we saw that because we said it was undefined here. So we have vertical asymptote at x equals 0, and then horizontal asymptote. What we do there, again, is we make sure that the highest order terms are first, which they already are, x squared and x squared. So this is 1 times x squared. So the horizontal asymptote is a line y equals 2 over 1, the ratio of leading coefficients. So it's y equals 2. So I'm just going to write that out without that middle part. So that's the horizontal asymptote. And we're skipping the symmetry part. So we need a piece of graph paper. Okay, so let's go back. Vertical asymptote, set denominator equal to 0. So we have still got more. The x-intercept was plus or minus 1.22. So let's go do that. Again, we'll use negative 10, positive 10, positive 10, negative 10. Okay. So 1.22 is going to be approximately there. Here's 1, here's 2, so it's about a quarter of the way. Okay, then we have vertical asymptote. Oh, we didn't have any y-intercepts. Okay, so we don't need to plot that. We do have a vertical asymptote, which is x equals 0. And then we have the horizontal asymptotes, which are going to be like this and like that. So one thing you'll notice is we have this x squared in the denominator. So we have a double root in the denominator. So even though I just show x equals 0, this is double. And the reason it's double is because I have x squared. So I really have x times x in the denominator. You know, if I go back to here, it's 2x squared minus 3 over x minus 0 times x minus 0. So you see I've got two roots. And as a consequence, these two asymptotes are going to go in the same direction. And because I have these horizontal asymptotes, most likely they're going to come underneath the asymptote and then go down. And is that true or not? Maybe not. Yeah, because the reason I'm thinking about this is if you look at this thing, they're both positive. So it should, so yeah, the question is, do you come down, you know, what are the options here? If I came down from the top, then I would cross this line, and then I would go through this point and have to come back up here, so that doesn't make any sense. So seems like it has to go that way. Just doesn't seem like it should go that way. I guess one thing you could do is pick some points here. And this thing looks like it's symmetric around the x-axis because these 2 points are symmetric. You've got the vertical asymptote. So if I evaluate the function at x equals 1, 2, 3, so let's do that. So what we want to do is look at f of 3, which probably should equal f of negative 3. And so what do we got? We got 2 times 3, squared minus 3 over 3 squared. So I'm just plugging 3 into this equation. So then you have 3 squared is 9 times 2 is 18. So you get 18 minus 3 over 9. So 18 minus 3, which is 15, divided by 9 is 1.66. And you can see if I plug f of negative 3 in there, so I did f of 3, you'd have 2 negative 3 squared minus 3 over negative 3 squared. Well, you're going to get the same number. Why? Because negative 3 squared is the same as positive 3 squared. So let's go here. We got 1, 2, 3, 1.66, which will put you about right there. Same way over here, negative 3, 1, 2, 3, 0.66. So yeah, it's got to go this way. So we'll come up here, go through this point, and start to curve till we get to go from underneath this thing. And we get this thing asymptote going both the same way. Okay, so let's evaluate this function. And I forgot what it was. Let's go over here and do it. 2x squared minus 3 over x squared. 2x squared minus 3 over x squared. And there you go. So it does look like what we just did. Okay. Next one. S over s squared plus 1. So we're going to find the intercepts. So the intercepts, the x-intercept, set the numerator equal to 0. And find the values of x where that's true, or s in this case. So s is the numerator, set that equal to 0. So in this case, our independent variable is s. So what we can say here is the point is going to be 0, 0. So the x value is 0 when the y value is 0. The y-intercept, you set x equal to 0. So we're going to do s of 0. So you have 0 over 0 squared plus 1, which is 0 over 1, which is 0. If we divide it by 0, it would be undefined, but 0 divided by any number is 0. So the y-intercept is going to be 0, 0. Yeah, surprise, surprise. So these are the same point. Okay, B, vertical asymptote. So the vertical asymptote is when denominator is 0. So we take the denominator, s squared plus 1, set equal to 0. S squared equals negative 1. Can't take the square root of a negative number, so no real zeros for this equation. So that means no vertical asymptotes. And the horizontal asymptote, use the rules again. So we rewrite this so it's, we take the original function here, and we've got s in the numerator. That's the same as, pardon me, s to the 1 power. If it was a constant, then it would be s to the 0, but it's s to the 1 over s to the 2 plus 1. So because 1 is less than 2, the horizontal asymptote is y equals 0. So that's my horizontal asymptote. there, in this case, there are no vertical asymptotes. Well, actually, that's what I said right there. No vertical asymptotes. So we've got an x and y intercept, which is the origin, and we have no vertical asymptotes, and we have a horizontal asymptote of 0. So this is definitely not going to give us enough without plotting some extra points. Okay, so here's our x and y intercept. And here is our horizontal asymptote, which we said was 0. Okay. So what is going on here? And there's no vertical asymptote, so you can imagine the thing looks kind of like maybe like, whoops, didn't do that. Maybe it goes up like this and back down again in either direction. It can't just be a straight line, so it's got to do something. If it starts down here and then it comes back down here, and it's not a straight line, it has to go up to some extent. So let's just go back and make sure we haven't made a mistake. Okay, so here's our function. S squared over, this is definitely 0. And the horizontal asymptote is definitely x equals y equals 0. Definitely no vertical asymptotes. There's an x-intercept, which could mean it's just touching it. Okay, so I think we got to pick some points out here. And, we don't need to do them too far away from the origin. The other thing is it is symmetric, so we probably can use that. So what we're going to do is evaluate this function, which we're calling g of s. So g of s is s over s squared plus 1. So let's do s of g of 1. So you get 1 over 1 squared plus 1, which is a half, because we get 1 squared, which is 1. 1 plus 1 is 2. Okay, so that's also equal to g of negative 1. So let's plot that. 1 a half, negative 1 a half. Let's do g of, let's pick like 3. G of 3 is going to be 3 over 3 squared plus 1, which is 3 over 10. 3 squared is 9. 9 plus 1 is 10. So that's 3/10, which is less than a half. So we got 1, 2, 3. 3/10 is about right there. And same thing about right there. So it looks like it's going to go up like this, and then it's going to kind of gradually decrease. So it kind of did look what I thought it had to look like. It's just it doesn't go up very much in the y direction. Let's put some scale in here. 10, negative 10, 10. So to actually get a better look at this thing, we probably should have adjusted the scale in the y direction. Well, let's just check it out. So we have, instead of s, I'm going to use x. So we got x squared, x over x squared plus 1. And we graph it. And, yeah, so it is actually isn't symmetric as I thought it was. I was assuming that that was true, but I should have realized that. Yeah. So now that I think about it, when this becomes squared, this changes. It doesn't change sign, but this one does. So what I could see is that g of negative s is going to be negative g of s. How do I know that? Well, if I do g of negative s, I'm going to have plug in negative s for s. So I get negative s over negative s squared plus 1, which is negative s over s squared plus 1, because when I square this, the negative sign becomes positive. So this is true, and hence it should have been symmetric around the origin. So instead of, this would be a half, this would be 3/10, so it kind of goes like that and then comes in at the bottom. So there you go. That's what it looks like. And if you wanted to zoom in the x in the y direction, you sort of see. So it increases rapidly here. It increases rapidly near the origin, but then it kind of dampens out. Okay, so those are those problems. Moving on to the next group. So all these had the most one vertical asymptote. Here's some more. These have more than one vertical asymptote. So this is number 8. So A is to find the x-intercept. So the x-intercept is when the numerator equals 0. And this is a point, x-intercept. So you get 3x is equal to 0, or x equals 0. So it's a point, so it's going to be 0. The y value is 0. That's what I'm doing. I'm setting the numerator equal to 0. And the x value, so the y value is 0, the x value is 0. So that's my x-intercept. And probably my y-intercept is going to be the same thing, because usually when the x-intercept is the origin, the y-intercept is the same thing. So the y-intercept, you set x equal to 0. So we're going to do f of 0, which is 3 times 0 over 0 squared minus 0 minus 2, which is 0 over negative 2, which is 0. So my y-intercept is going to be x equals 0, so that's the x equals 0 here, comma, y equals 0. So that's what we thought it was going to be. It's going to be the origin. Okay, next. Vertical, horizontal asymptotes. So the vertical asymptote that's when the denominator equals 0. Denominator is 0 as long as the numerator is not 0 of the same value. So in this case, when you have a quadratic, you're going to factor that. So we're going to take the unfactored version, and then we're going to see if we can factor it. So our first term is going to be x. What two numbers multiplied together give you 2? So then you have 1 and 2. Now because this is negative, it's the difference between the two that has to be this. So if you take 2 minus 1, you'll get 1. So I know that's going to work out. I've just got to decide whether I have positive 1 and negative 2 or the other way around. So since I have a negative in the middle, the bigger part of the product of these last two numbers has to be negative. So what I'll get is that x minus 2 will force this to go to 0, and x plus 1 equal to 0 will force it to go to 0. So I get the values of x equals 2 and x equals negative 1. And those are the equations. Not only are they the values of x which cause the denominator to go to 0, they're also the lines that correspond to the vertical asymptotes. Okay, and then you have horizontal asymptotes. So again, you're looking at the highest order term. So we look at f of x is 3x to the first power over x to the second power minus x to the first power minus 2 times x to the 0. And I'm just putting those in there to show that, you know, this is the highest order term and this is the highest order term with its corresponding coefficients. Now, because the numerator is less than the denominator, under those circumstances, the horizontal asymptote is a line y equals 0. If these are equal to each other, then you take the ratio of the leading coefficients. If it's the other way around, if this is higher than that, then there is no horizontal asymptote. Okay, so we've got our x and y intercepts, which is the origin. Got two vertical asymptotes and a horizontal asymptote. So we're now going to plot those and see what other points we might need. So again, let's go from -10 to +10, -10 to +10. Okay, so the origin is my intercept. It's going to go through one way or the other. We've got two vertical asymptotes, one at +2, x equals +2, which is this line, and x equals -1, which is that one. And then we've got a horizontal asymptote, which is 0. So we can draw a line here and a line there. We don't need to draw inside the asymptotes because the horizontal asymptote is what's happening out here. Now, the question is, does it go like this? Does it go like that? Likewise in the other way. So at this point, we probably want to pick 2 points. Now I can figure out which way it goes, and I'll tell you why after we do this, but let's just, we know that it has to go through here, the origin, either this way or that way. And we also know that if we have single roots in the denominator, which we do, that on one side of the vertical asymptote it has to go up, and on the other side it has to go down. If you have double roots, then it goes either both up or both down. If you have an even root, it's kind of like with intercepts almost. If you have separate values, single roots, then you have, in the case of x-intercepts, you have one x-intercept. If you have two, if you have a multiplicity of roots of even, then it's going to just touch it. So the same thing is kind of true here. If you have single vertical asymptotes or a single 0 at a vertical asymptote, then it goes up one side and down the other. It's always opposite. So let's pick a value. This is x equals 2. We're going to evaluate the function at do f of 3. That's going to be right here. So the one thing it'll do is it'll tell us whether it's on either which side of this horizontal asymptote and how high it is. So we want that. We could do f of 1. That would help us know what's going on inside the two asymptotes, f of 1, and then we'll do one over here, which is going to be f of -2. That would be over. So we're going to pick these three values of x, evaluate the y value. Okay, so what is the function? Again, 3x over x squared minus x minus 2. So we have 3x squared over x squared minus x minus 2. So we get 3 times 3 over 3 squared minus 3 minus 2. So that's 9 over 9 minus 3 minus 2, which is 9 over 4. So 9 minus 5 is 4. So we can plot that point. So we go 9/4. So 8/4 is 2, so it's going to be right there. We can do f of 1. So we do 3 times 1 over 1 squared minus 1 minus 2. So in the numerator we have 3. In the denominator we have -2. 1 minus 1 is 0. So you get -1.5. So we can plot that. So here's x equals 1, y equals -1.5. And then we can do f of -2. So we get 3 times -2 over -2 squared minus 2 minus 2. So plugging in -2 for x. So in the numerator I get -6. Here I'll get 4. Something's wrong here. Reason I'm going, because I get, oh, yeah. See, I was getting a vertical asymptote there, and I knew I didn't have one, so I thought I must have done something wrong, which I had, because you have 4, -2 squared minus and -2 minus 2, so I had to, so that's, you get 4, -2 squared is 4, plus 2 minus 2. So that'll give you -6 over, so these cancel out, 4, -3/2. So that's going to be -3/2, put you right there. Okay, so now, because this is above the x-axis and I don't have any x-intercepts here, I know it has to keep going up, so it's going to go up like this to the vertical asymptote. Now it's going to come down here and it's going to approach the horizontal asymptote like that. Now because, for 2 reasons. One is because I have a single 0 in the denominator. I know that this has to come from this direction. But I would have known that anyway because these 2 red points have to be connected, and they can't be connected except going up in this direction. So that's what happens. And then again, because I have a single 0 here, it's going to come down here to -infinity, which I knew already because of my points here. So I have to start down here so I can get up to there. And then it's going to approach this horizontal asymptote like that. Okay, so here's my equation, and I forgot what the function was already. There it is. So let's just move this out of the way so we can plot this thing. Okay, so you got 3x divided by x squared minus x minus 2, close parenthesis, graph this thing. Let's zoom out so we can get from 10 to 10 in that direction, and the same thing in the other direction. So there we go. Let's pull that over. So there you can see. So there's the x-intercept, horizontal asymptote of 0, vertical asymptotes at -1 and +2. So looks good. Okay. Now this last one, I'm sure you had to come and look at this solution. I'm just going to show you that it's the same basic idea. So you're going to have the x-intercepts. So that's where you set the denominator is 0. What values of x make the denominator equal to 0? Well, we just had the same value here, except now it's in the numerator. And it's not denominator, it's numerator. Let's fix that. Numerator, the top. So the numerator is the same as the denominator in the previous problem. So we know we can factor that. It's going to be x minus 2 times x plus 1. So we get x equals 2 and x equals -1. In this case, we're talking about intercepts. So it's going to be 2, 0 and -1, 0. So they're not intercepts. They're intercepts, not vertical asymptotes. Okay, the y-intercept, you set x equal to 0. So what we're doing g of 0, which is 0 squared minus 0 minus 2 divided by 0 cubed minus 2 times 0 squared minus 5 times 0 plus 6. We can see the only thing is that we are non-zero are the last terms, and you could simplify that down to 1/3. So we got x equals 0, y equals -1/3. So those are my x-intercepts. This is my y-intercept. Okay. Next thing we do is the asymptotes. So B. So vertical asymptotes, that's when the denominator goes to 0. Denominator. And the numerator is non-zero. So the x value is where this occurs. So we'll set the denominator equal to this. Okay, so now we're having to use stuff we learned in the previous section, zeros of polynomials. So, remember the rational zeros can be plus or minus. What you do is take the factors of 6. So it's plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And the denominator can be plus or minus 1. So that just means you've got 6 possibilities. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. We know most likely they're not going to, x probably is not going to be equal to 2 or equal to negative 1, because that's where the vertical asymptotes are. So, it could happen, but it's not likely to happen. So what I would do is I'd try 1. 1's always a good choice when it comes to solving a polynomial. So I put the coefficients up here. So I got 1, negative 2, negative 5, 6. So let's put 1 in there. Bring the 1 down. 1 times 1 is 1. Add these together, you get negative 1. Negative 1 times 1 is negative 1. Negative 5 plus negative 1 is negative 6. 1 times negative 6 is negative 6. You add these two together, you get 0. So this is going to be x. X equals 1 is 1, 0. So the factor is x minus 1. And what we're left with is x squared minus x minus 6. And hopefully at that point you can then factor it however you want to factor it. First choice is to do it by observation. So, because this coefficient is 1 in front of the x squared, we're going to just have x. What two numbers multiplied together give you 6? 1 and 6, 2 and 3. This is negative, so we're going to subtract the 2. So you got 3 minus 2 or 2 minus 3. Well, that equals 1, so this is not going to work because this one does work. So 1's going to be 2, 1's going to be 3. Because this is a negative quantity, the negative sign goes with the bigger of the 2 and the positive. So what that means is from this we have 3 vertical asymptotes. Let's move this thing down again. So you've got the vertical asymptotes are when each factor goes to 0. So what we'd say is, x minus 1 equals 0, x plus 2 equals 0, x minus 3 equals 0. So we get x equals 1, x equals negative 2, x equals positive 3. So those are the equations for my vertical asymptotes. And then finally, the horizontal asymptotes. So that's the rules here. So if you look at the function, x squared minus x minus 2 over x cubed minus 2x squared minus 5x plus 6. So you take the two highest order terms, these two. In this case, well, again, in this case, 2 is less than 3. So that means y equals 0 is the line. if these were even, if they were both cubed, then it'd be 1 divided by 1. If it was 3 and 2, then you wouldn't have any horizontal asymptote. Okay, so let's insert a page right here, and we'll bar stuff from either side. So we're going to need to add a page. Okay, let's put -10, +10, +10, -10. Okay. So let's do the zeros first. So you're going to have a 0 at 2, 0. You have a 0 at -1, 0. We have a y-intercept at 0, -1/3. Okay, come over here. Vertical asymptotes. So vertical asymptote at +1, that's right here. A vertical asymptote at -2, it's right there. Vertical asymptote at +3. So you can see none of the zeros correspond to the asymptote. So those are all our points. Now we have single vertical asymptotes. So we didn't have multiple roots here. So we know that they're going to switch over. We also have our horizontal asymptote here, which is 0. So we're going to draw a horizontal line here and a horizontal line there. So this one's probably going to look like that. And this one's going to go like this. So you could figure out, I mean, you could use some logic here, but the best thing to do is to evaluate the function at maybe this value of x and this value of x, which is going to be 1, 2, 3, 4. So we're going to do f of 4 and 1, 2, 3, f of -3. So those are 1 unit outside the vertical asymptotes, the ones that are outside them. And now we just need to copy this equation so I can evaluate the function. Okay, so there we go. And it's g, not f. So we do g. G of 4, g of -3. G of 4, g of negative, okay. So we get 4 squared minus 4 minus 2 divided by 4 cubed minus 2 times 4 squared minus 5 times 4 plus 6. So let's evaluate each term. So 4 squared is 16, minus 4 minus 2. 4 cubed is 64. Then we have 2 times 4 squared. 4 squared is 16. 16 times 2 is 32. -5 times 4 is -20. Plus 6. So we're going to have 16 minus 6, which is 10. And then we have 64 minus 32, which is 32. 32 minus 20 is 12. 12 plus 6 is 18. That simplifies down to 5/9. Okay, so we've got a point 4, 5/9. And then we could do -3. So we have -3 squared minus -3 minus 2 divided by -3 cubed minus 2 times -3 squared minus 5 times -3 plus 6. Okay, let's move this down. So let's evaluate each term. So -3 squared is 9, minus 3 minus 2. The denominator we have -3 cubed, which is -27. We have 9 squared, 3 squared, which -3 squared, which is 9. 9 times -2 is -18. 5 times -5 times -3 is plus 15 plus 6. So in the numerator, we have 9 minus 5, which is 4. And here we have 27, 37, 45, -45. Plus 15 is -30. Plus 6 is -24. So that's going to be -1/6. So the point we have is -3, -1/6. Okay, so let's plot those 2 points. So this is going to be 5/9. That's a little over a half. And this one here is going to be -1/6. It's going to be really close to that. Okay, so now we can draw what's going on. So this is above the horizontal asymptote, so it's going to come along here. And of course it takes this quick turn to go up. Can't go down because then I have an x-intercept. Now because this is going up, it's going to come back the other direction on the other side of the asymptote. So it comes up, and then at some point it goes through here, and it keeps going up like that. Can't loop back down because there's only one x-intercept. So this goes up to the top, so it's going to come down to the bottom again. And then it's going to come up along the asymptote through these 2 points, both the y and x-intercept, and then it'll go all the way up here like that. And this bops down to here, and it goes up really close to the vertical asymptote, and it goes to this point, and then it has to quickly approach the horizontal asymptote. So these things are really close to the axes. Okay, so that's what it looks like, and now we will need to find the equation so I can plot it. So what we're going to have is x squared minus x minus 2, all divided by x cubed minus 2 times x, 2x squared minus 5x plus 6, close parenthesis. Graph this thing. There it is. Okay, so let's get it so we can see what this thing looks like. So you can see how quickly these things approach the horizontal asymptotes. You see how here it crosses the y-axis at about y equals 0.3 something. What did I say it was? The y-intercept was somewhere here. Y-intercept -1/3. So is that what we got here? If we zoom in to right here, you see it's negative about 0.333. Yep. Okay, so that's that problem. Okay, and the last 3 problems are slant asymptotes. So slant asymptotes are where you don't have a horizontal asymptote, but you do have a linear result that you can use as an asymptote. So it's very similar, except when you get to, instead of doing vertical and horizontal asymptotes, you do slant asymptotes. Now, the way the slant asymptote works is you use long polynomial division to determine that. But let's first do the intercept. So the x-intercept is when the denominator is 0. So in this case, when does 2x squared plus 1 equal 0? Well, that's when 2x squared equals -1, which never happens, because anytime you square a number, you're going to get a positive number. So there are no x-intercepts with this. The y-intercept, you set x equal to 0. So you're doing f of 0 in this case. So you have 2 times 0 squared plus 1 over 0, which is 1 over 0, which is undefined. So this one, there are no x-intercepts because there are no real zeros. Here, there are no y-intercepts because it's undefined. Okay, so that is intercepts. Now, vertical asymptotes. So that is where the vertical asymptotes are, where the denominator, did I write numerator out here? I did that again. I thought I remember something, where the numerator is 0. It's probably something good to write down. Denominator, okay, is 0. What values of x does that occur? Well, you just set the denominator, which is x, equal to 0. So that's the equation of the vertical asymptote at x equals 0. It's a vertical line. Okay, now the slant. So what you do is you take your numerator, make sure you put a 0 in there for if anything's missing, and you divide that by the denominator. So what do I multiply x by to get 2x squared? Well, the answer is 2x. So 2x times x is 2x squared, but I'm subtracting that. I don't have any extra stuff because it's just x here. So when I subtract that, I get 0. I bring this down, and then I say, what do I need to multiply x by to get 0x? Well, the answer is 0. So 0x times 0 is 0. I'm subtracting that. What I'm left with is a remainder of 1. So one thing you can say is that if you take this, you'll get 2x plus the remainder over the original expression. Okay, so when I talk about the horizontal, I mean the slant asymptote, the slant asymptote is the equation. You take this and you say y equals that. So don't just put 2x in this case. It's y equals 2x. The slant asymptote, just like the vertical asymptote is x equals 0, the slant asymptote is y equals 2x. So horizontal asymptote, you have y equals something, 0 or some number. In this case, slant asymptote, you got y equals some function of x, some linear function of x. Okay. So now we are going to plot what we know. So we'll take our graph paper, and again we'll go from -10 to +10. So the x-intercept is where, there were no x and y-intercepts. The only thing we have is this, well, we have vertical asymptote. Okay, so let's write that. The vertical asymptote is just x equals 0, so that's that. And then we have this slant asymptote, which is y equals 2x. So that's going to look like this. You're going to go through the origin, and you're going to have a slope of 2, and it's going to go either side of this. So there we go. So that's the line y equals 2x, and this is the line x equals 0. Okay, so the question is, it's got to approach this this curve. Well, if I did it like that, that wouldn't be a function, so that makes no sense whatsoever. So one other option is if this is a y-intercept and this is, you come down, but then instead of going horizontally, you go back up again. And the same thing would be true here. In this case, you do have a function because you can use the vertical line test. So it makes sense that it's supposed to look something like that. So if I were to pick a value of x, additional values to evaluate, I would probably evaluate at +1 and -1, because that looks like somewhere in between this transition from coming down to going back up again. So let me get rid of those, just kind of approximations. So remember the function is 2x squared plus 1 over x. So f of x equals 2x squared plus 1 over x. I think that's right. 2x squared plus 1 over x. Okay. So what we're going to do is f of 1. So that's 2 times 1 squared plus 1 over 1, which is, that's 2. 1 squared is 1. 2 times 1 is 2. So that's going to be 3 over 1. So x is 1, y equals 3. And we're going to do f of minus 1, which is going to be 2 times -1 squared plus 1 over -1, which is going to be -1 squared is +1, so 2 times +1 is 2 plus 1. So you get 3 over -1. This is equal to 3. This is equal to -3. So we have -1, -3. So we can plot those points. 1, 1, 2, 3. So that's the point right there. -1, 1, 2, 3. So with that, we probably could draw a reasonable thing. We come down here, this vertical asymptote, we come through that point, and then we loop back up along the slant like that, and you can do the same thing. We come along the slant and go through this point. Now we don't know exactly where that point turns around, but at least this gives us some idea of what it looks like. And if we plot this function, we have 2x squared plus 1 divided by x. We graph it, and let's zoom out here. So we go to 10 and do the same thing in this direction. There we go. And we can also plot this slant asymptote, which is y equals x. So I'm just going to put x in there. And something, oh, it's y equals 2x. Yeah, sorry. Y equals 2x. 2x. Okay, so there you can see. Now they look pretty similar. Here's the point, 1, 3, and you see that it actually does go down a little bit further, and that's what calculus would tell us. It would tell us exactly what the value of x is for this to occur and this to occur. So, we get a pretty good estimate. We're not as accurate as we could be. Okay, next one, similar kind of thing. The numerator, actually it's probably too similar. So, the only difference here is that the slant is going to be different. It's not going to have any, it's going to have a vertical asymptote at x equals 0, and there are no roots. So the only thing difference you can copy down from the previous problem just is what is the slant is going to be different. So you have x squared plus 0x plus 1 divided by x. What do I need to multiply x by to get x squared? The answer is x. X times x squared. X times x is x squared. We're subtracting that. So that goes to 0. Bring the 0 down. What do I need to multiply x by to get 0x? The answer is 0. And then you bring this down. That's your remainder. So this is the same as x plus 1 over x. So the only difference is that my slant asymptote instead of y equals 2x is y equals x. So let's plot those. We may want to pick a different point based on how this thing looks as far as the points, the extra points that we use. I didn't want to do that. Okay, here's a graph paper. Okay, so we still have vertical asymptote x equals 0. In this case, the slant asymptote is this line. So this is y equals x. This is y equals 2x. So, if I pick 3, or x equals 1, yeah, still might be okay. I can just evaluate the function at positive 1 and negative 1. So let's do that over here. So the function was equal to x squared plus 1 over x. So f of 1 is 1 squared plus 1 over 1, which is 2 over 1, which is 2. And we could do f of negative 1, which would be negative 1 squared plus 1 over negative 1. So the numerator is still 2. The denominator is negative 1, so you get negative 2. So this is 1 comma 2, and this is negative 1 comma negative 2. So those are the 2 points. So you go 1 comma 2, the point right there, negative 1, negative 2. And again, you can sketch this thing in like that and like that. Okay, I think I'll change that next time and make it a different one. Okay, now the last one is more difficult. It's also going to have some x-intercepts. So let's go slower on this one. So a x-intercept. That's where the numerator, make sure I got that right this time, numerator is 0. Okay, so set the numerator equal to 0. Okay, so what are the ways we could try this out? You could just try inspection. Let's see what, the first 2 things have to be 2x and x. And then the last 2 have to be 5 and 1. So if I did, let's just try one and the other, see what happens. So, and this is positive, so these would they'd either be both negative or both positive. So we had 5 plus 4 is 9, which is not 5, so it's not going to work out. So that's not going to work. Because the first term is a 2, it might make more sense to use the quadratic formula. So I'm going to say a is 2, b equals negative 5, c equals 5. So we get x is equal to minus b plus or minus the square root b squared minus 4ac over 2a. So we get negative a negative 5 plus or minus the square root of negative 5 quantity squared minus 4 times a, which is 2, times c, which is 5. And I'm just hesitating because I'm getting a negative result. So that must mean there are no x-intercepts. Is that right? Minus b plus minus b squared minus 4ac. So I got 25 here, and then I subtract 40. Gives me a negative number. So it's not going to work. Okay, so there are no x-intercepts. Okay, y-intercept. Set x equals 0. Okay, I'm not going to mess around with putting zeros in. You just take the two constant terms because of the other ones that go to 0. So you get a point which is going to be 0 comma negative 5 halves. So that's my y-intercept. Okay. The next thing you've got is vertical asymptotes. So that's part B, vertical asymptotes. That's where the denominator equals 0. So we get x equals 2, which is an equation for a vertical line. So that's perfect. Okay, so we're going to plot what we have so far. So this was actually not as bad as I thought. Okay, we still need to do the slant asymptote. So let's go back and do that before we get too far along here. So the slant asymptote. So we're going to just have a little more difficult polynomial division, but it's not terrible. So we'll have 2x squared minus 5x plus 5 and x minus 2. Okay, so what do I need to multiply x by to get 2x squared? 2x. So I take 2x times x, which is 2x squared. I take 2x times negative 2, which is negative 4x. I'm really subtracting those. So these go to 0, and therefore I have negative 5 plus 4, so that's negative 1x. And then I add 5, bring down the 5. What do we need to multiply x by to get negative x? It would be negative 1. So negative 1 times x is negative 1x. Negative 1 times negative 2 is positive 2. I'm really subtracting that. So these go to 0, and I have 5 minus 2, which is 3. So that's my remainder. So if I wanted to, I could rewrite this as 2x minus 1, and then you take the remainder and divide by the original denominator. The whole idea of the slant asymptote is when x gets very large, this thing ratio goes to 0, and you're just left with the equation. So my slant asymptote is y is equal to 2x minus 1. So that's my slant asymptote. Okay, so let's do what we know. Okay, there are no x-intercepts. The y-intercept is negative 5 halves, which is right here. Okay, well, we also need to plot the vertical asymptote, which is a vertical line at x equals 2. And we have the the slant asymptote, which is 2x minus 1. So we go through the x-axis at negative 1, the y-axis at negative 1, and we have a slope of 2. So you go over 2, up 2, over 2, up 2, and you can keep doing that. And then once you've got that all straightened out, you can then stretch it the other direction. So it's going to look something like that. So this curve here is y equals 2x minus 1. This is x equals 2. And you see we've got 1 point right there. But let's pick two other values of x. X equals 1 and x equals 3. This should give us a point somewhere up in this little quadrant. And this one will give us a little better idea of where it extends to. Let's find the function again here. So we want to do it at 1 and 3 on either side. So we want to do f of 1. So we'll have 2 times 1 squared minus 5 times 1 plus 5 divided by 1 minus 2. So you can see these cancel out, and I get 2 divided by negative 1, which is negative 2. So let's see if that makes any sense. So that was f of 1, and we said that ended up being -2. So let's plot that. So f of -1 is 2, okay, or -2. And then we're going to do 3. So f of 3 is 2 times 3 squared minus 5 times 3 plus 5 divided by 3 minus 2. So the denominator is 1, and in the numerator we get 9 times 2, which is 18. 18 minus 15 is 3. 3 plus 5 is 8. So I get 8. So it's 3 comma 8. So I'm come over here, 3 comma 8. 1, 2, 3, 4, 5, 6, 7, 8. So we can draw this function to look something like this with the vertical asymptote at x equals 2. Okay, so let's plot that thing out. And actually I've already done that. So there it is. Let me zoom out a little bit in the x direction. Okay, so you can see the similarity. Here's the vertical asymptote would be at x equals 2. And we evaluated the function at 1, which put us about right there, so that was a good choice, and at 3, which would put us right there. So those were good choices for that extra point. So that is it, I believe. I don't think there's any more problems. Okay.